Greetings to all and welcome back to the course devoted to the basics of molecular geometry and chemical bonding. Although the bonding theories you have seen so far provide simple and effective ways for us to visualize molecules and predict their shapes and bond angles, Lewis structures and valence bond theory do not enable us to describe or predict some important properties of molecules. For example, diatomic oxygen exhibits a property called paramagnetism. Paramagnetic species are attracted by magnetic fields, whereas diamagnetic species are weakly repelled by them. You might recall from the lecture on electron configuration of atoms that such magnetic properties are the result of a molecule's electron configuration. Species in which all the electrons are paired are diamagnetic, whereas species that contain one or more unpaired electrons are paramagnetic. Since the molecule of oxygen exhibits paramagnetism, it must contain unpaired electrons. However, according to the Lewis structure of oxygen and the valence bond theory description of this molecule, all the electrons in oxygen are paired. So, a more advanced bonding theory is needed to describe the paramagnetism of oxygen and other important molecular properties. The focus of the present lecture will be on one of the most advanced theories of bonding, commonly called molecular orbital theory. According to molecular orbital theory, the atomic orbitals involved in bonding combine to form new orbitals that are the property of the entire molecule, rather than of the atoms forming the bonds. These new orbitals are called molecular orbitals. In molecular orbital theory, electrons shared by atoms in a molecule reside in the molecular orbitals, which are similar to atomic orbitals in several ways. In particular, they have specific shapes and specific energies, and they can each accommodate a maximum of 2 electrons. As with atomic orbitals, 2 electrons residing in the same molecular orbital must have opposite spins, as required by the Pauli exclusion principle. And, like hybrid orbitals, the number of molecular orbitals we get is equal to the number of atomic orbitals we combine. Please note that our treatment of molecular orbital theory in this course is limited to descriptions of bonding in diatomic molecules consisting of elements from the first 2 periods of the periodic table. For further details, you should take more advanced courses in chemistry. To begin our discussion, we should consider the hydrogen molecule, the simplest homonuclear diatomic molecule. According to valence bond theory, a hydrogen molecule forms when 2 hydrogen atoms are close enough for their 1s atomic orbitals to overlap. Whereas, according to molecular orbital theory, 2 hydrogen atoms come together to form a hydrogen molecule when their 1s atomic orbitals combine to create molecular orbitals. This figure shows the 1s atomic orbitals of the isolated hydrogen atoms and the molecular orbitals that result from their constructive and destructive combinations. If what you see here surprises you, try to recall what you learned in the 7th module when I introduced you to quantum theory. Remember that the quantum mechanical approach treats atomic orbitals as wave functions since electrons showcase properties of both waves and particles. One of the properties of waves is their capacity for constructive combination and destructive combination when the wave functions describing the combining electrons have opposite signs. The constructive combination of the 2 1s orbitals gives rise to a molecular orbital that lies along the internuclear axis, directly between the 2 hydrogen nuclei. Just as electron density shared between 2 nuclei in overlapping atomic orbitals draws the nuclei together, electron density in a molecular orbital that lies between 2 nuclei will also draw them together. Thus, this molecular orbital is referred to as a bonding molecular orbital. The destructive combination of the 1s atomic orbitals also gives rise to a molecular orbital that lies along the internuclear axis, but this molecular orbital, which consists of 2 lobes, does not lie between the 2 nuclei. Since there are no negatively charged electrons between the two positively charged nuclei in an antibonding orbital, the two combining atoms would actually pull each other in opposite directions, rather than toward each other. The molecular orbital with no electron density between the nuclei is referred to as an antibonding molecular orbital. Molecular orbitals that lie along the internuclear axis, such as the bonding and antibonding molecular orbitals in hydrogen, are also referred to as sigma molecular orbitals. Note that the designations sigma and pi are used in molecular orbital theory just as they are in valence bond theory. Sigma refers to electron density along the internuclear axis, and pi refers to electron density that influences both nuclei but does not lie directly along the internuclear axis. More specifically, the bonding molecular orbital formed by the combination of two 1s atomic orbitals is designated sigma 1s, and the antibonding orbital is designated sigma star 1s, where the asterisk distinguishes an antibonding orbital from a bonding orbital. Like atomic orbitals, molecular orbitals have specific energies. The combination of two atomic orbitals of equal energy, such as two 1s orbitals on two hydrogen atoms, yields one molecular orbital that is lower in energy and one molecular orbital that is higher in energy than the original atomic orbitals. As you can see, the bonding molecular orbital in the hydrogen molecule is concentrated between the nuclei along the internuclear axis. Electron density in this molecular orbital both attracts the nuclei and shields them from each other, stabilizing the molecule. Thus, the bonding molecular orbital is lower in energy than the isolated atomic orbitals. In contrast, the antibonding molecular orbital has most of its electron density outside the internuclear region. Electron density in this orbital does not shield one nucleus from the other, which increases the nuclear repulsions and makes the antibonding molecular orbital higher in energy than the isolated atomic orbitals. Showing all the molecular orbitals in a molecule can create a very complicated picture. Therefore, rather than represent molecules with pictures of their molecular orbitals, we generally use diagrams in which molecular orbitals are represented with boxes placed at the appropriate relative energy levels. For instance, the following figure shows the energies of the sigma 1s and sigma star 1s molecular orbitals in the hydrogen molecule, relative to the energy of the original 1s orbitals on the two isolated hydrogen atoms. Like atomic orbitals, molecular orbitals fill in order of increasing energy. Note that the electrons that originally resided in the atomic orbitals both occupy the lowest energy molecular orbital with opposite spins. We can also construct a similar molecular orbital diagram for the hypothetical helium-2 molecule. Like the hydrogen atom, the helium atom has a 1s orbital. However, unlike hydrogen, the 1s orbital on helium has two electrons, not one. The combination of 1s orbitals to form molecular orbitals in the hypothetical helium-2 molecule is essentially the same as what I have described for the hydrogen molecule. With molecular orbital diagrams, such as those for hydrogen and the hypothetical helium-2 molecule, we can begin to see the power of molecular orbital theory. For instance, for a diatomic molecule described using molecular orbital theory, we can calculate the bond order. The value of the bond order qualitatively indicates how stable a molecule is. The higher the bond order, the more stable the molecule. Bond order is calculated using the formula presented below. In the case of hydrogen, where both electrons reside in the sigma 1s orbital, the bond order is 1. In the case of helium-2, where the two additional electrons reside in the antibonding sigma star 1s orbital, the bond order is 0. Molecular orbital theory predicts that a molecule with a bond order of 0 will not exist, and helium-2, in fact, does not exist under ordinary conditions. We can perform similar analyses for hypothetical diatomic molecules like lithium-2 and beryllium-2. The lithium and beryllium atoms have ground state electron configurations of helium-2s1 and helium-2s2, respectively. In these atoms, the 2s atomic orbitals also combine to form the corresponding sigma and sigma star molecular orbitals, and the following figure shows the molecular orbital diagrams and bond orders for lithium-2 and beryllium-2 molecules. Please note that when we draw molecular orbital diagrams, we only need to show the valence orbitals and electrons. So, as molecular orbital theory predicts, lithium-2, with a bond order of 1, is a stable molecule, whereas beryllium-2, with a bond order of 0, does not exist. To consider diatomic molecules beyond beryllium-2, we must also consider the combination of p-atomic orbitals. Like s orbitals, p orbitals combine both constructively to form bonding molecular orbitals that are lower in energy than the original atomic orbitals and destructively to form antibonding molecular orbitals that are higher in energy than the original atomic orbitals. However, the orientations of px, py, and pz orbitals give rise to two different types of molecular orbitals, sigma and pi. Sigma molecular orbitals have regions of electron density in the bonding and antibonding molecular orbitals lying along the internuclear axis. In contrast, pi molecular orbitals have regions of electron density affecting both nuclei, but not lying along the internuclear axis. To elaborate, orbitals that lie along the internuclear axis and point directly toward each other combine to form sigma molecular orbitals. In the top right corner of the screen, you can see not only the shapes of the sigma molecular orbitals generated from p-atomic orbitals, but also their relative energies compared to each other and the starting atomic orbitals. Atomic orbitals that are aligned parallel to each other, like the py and pz orbitals, combine to form pi molecular orbitals. Please note that the corresponding antibonding molecular orbitals are designated as pi star to distinguish them from the bonding orbitals. Here you can see the constructive and destructive combinations of parallel p orbitals, as well as the locations of the molecular orbitals relative to the two atomic nuclei. Again, electron density in the resulting bonding molecular orbitals serves to hold the nuclei together, whereas electron density in the antibonding molecular orbitals does not. Just as the p-atomic orbitals within a particular shell are higher in energy than the s orbital in the same shell, all the molecular orbitals resulting from the combination of p-atomic orbitals are higher in energy than the molecular orbitals resulting from the combination of s atomic orbitals. In general, molecular orbital theory predicts that the more effective the interaction or overlap of the atomic orbitals, the lower in energy the resulting bonding molecular orbital will be, and the higher in energy the resulting antibonding molecular orbital will be. To better understand the relative energy levels of the molecular orbitals resulting from p-orbital combinations, let's consider the molecule of fluorine. The electron configuration of fluorine is helium-2s2, 2p5. It has just one unpaired electron in one of the two p orbitals. If we allow the four atomic orbitals in two fluorine atoms to overlap, it will generate 8 molecular orbitals. Interestingly, 7 out of the 8 formed molecular orbitals will cancel each other out, as we have both the bonding and antibonding orbitals filled with electrons. Here, the only bonding molecular orbital that remains is the sigma 2p orbital, as the bond order in the molecule of fluorine is 1. To summarize, the relative energy levels of molecular orbitals in fluorine can be represented by the diagram presented here. The p orbitals that lie along the internuclear axis overlap most effectively giving the lowest energy bonding molecular orbital and the highest energy antibonding molecular orbital. For the molecule of fluorine, the order of orbital energies assumes that p orbitals interact only with other p orbitals and s orbitals interact only with other s orbitals. In other words, there is no significant interaction between s and p orbitals. However, the relatively smaller nuclear charges of boron, carbon, and nitrogen atoms cause their atomic orbitals to be held less tightly than those of atoms with larger nuclear charges. For these elements, some sp interaction does take place, resulting in changes in the relative energies of the sigma 2p and pi 2p molecular orbitals. Although energies of several of the resulting molecular orbitals change, the most important change is that the energy of the sigma 2p orbital becomes higher than that of the pi 2p orbitals. Beginning with oxygen, the nuclear charge is sufficiently large to prevent the interaction of s and p orbitals. Thus, for the diatomic molecules of oxygen and neon, the order of molecular orbital energies is the same as that for fluorine. The following figure gives the molecular orbital diagrams, magnetic properties, bond orders, and bond enthalpies for real and hypothetical diatomic molecules of boron, carbon, nitrogen, oxygen, fluorine, and neon. Note that the filling of molecular orbitals follows the same rules as the filling of atomic orbitals, that is, lower energy orbitals fill first. Each orbital accommodates a maximum of 2 electrons with opposite spins, and finally, Hund's rule is obeyed. There are also several important predictions made by the molecular orbital diagrams presented here. First, molecular orbital theory correctly predicts that neon 2, with a bond order of 0, does not exist. Second, it correctly predicts the magnetic properties of the molecules that do exist. Both diboron and the molecule of oxygen are known to be paramagnetic. Third, although bond order is only a qualitative measure of bond strength, the calculated bond orders of the molecules correlate well with the measured bond enthalpies. For instance, the nitrogen molecule, with a bond order of 3, has the largest bond enthalpy of the 6 molecules. In contrast, the molecules of boron and fluorine, each with a bond order of 1, have the smallest bond enthalpies. It is the ability to correctly predict the properties of molecules that makes molecular orbital theory a powerful tool in the study of chemical bonding. What you have learned so far about molecular orbital theory can also be applied to heteronuclear diatomic species, in which the 2 atoms are different, such as nitric oxide. Let's start with the electron configurations of the oxygen and nitrogen atoms, focusing on their valence electrons. In a case such as this, our description of the molecular orbitals involved in bonding must be modified slightly. First of all, you already know that the atomic orbitals of a more electronegative atom are lower in energy than the corresponding atomic orbitals of a less electronegative atom. Accordingly, the 2s and 2p atomic orbitals are lower in energy for oxygen, which is more electronegative than nitrogen. Altogether, we have 8 atomic orbitals, which combine to give us 8 molecular orbitals. If we now fill in the molecular orbitals with the electrons from the atomic orbitals, we will get the following picture. Note that in molecular orbitals, not all electrons are paired, as we end up with an unpaired electron in one of the antibonding orbitals. It should be noted that when atomic orbitals of different energies interact to form molecular orbitals, the lower energy atomic orbital contributes more to the bonding molecular orbital, and the higher energy atomic orbital contributes more to the antibonding molecular orbital. The result is that the bonding molecular orbital more closely resembles the atomic orbital of the more electronegative atom, and the antibonding molecular orbital more closely resembles the atomic orbital of the less electronegative atom. In other words, the electron density in the resulting bonding molecular orbital is greater in the vicinity of the more electronegative atom, in this case oxygen. This also means that the unpaired electron in one of the antibonding orbitals spends more time around nitrogen. In addition, recall that the order of energies of molecular orbitals in second-period homonuclear diatomic molecules is different for nitrogen and oxygen. For second-period heteronuclear diatomic species containing one atom from each group, such as nitric oxide and carbon monoxide, there is no simple rule that can tell us the order the molecular orbitals follow. However, note that the molecular orbitals in nitric oxide follow the same order as those in nitrogen. You saw that often. The bond order determined from a molecular orbital diagram corresponds to the number of bonds in the Lewis structure of the molecule. Nevertheless, in the case of nitric oxide, the Lewis structure contains a double bond, whereas the molecular orbital approach gives a bond order of 2.5. In fact, the molecular orbital approach gives a bond order that is more consistent with experimental data, as nitric oxide is a paramagnetic gas due to an unpaired electron in one of its non-bonding pi orbitals. To sum it up, in this lecture, you were introduced to molecular orbital theory, which describes bonding in terms of the combination and rearrangement of atomic orbitals to form orbitals associated with the molecule as a whole. You saw that bonding molecular orbitals increase electron density between the nuclei and are lower in energy than the individual atomic orbitals, whereas antibonding molecular orbitals have a region of zero electron density between the nuclei and an energy level higher than that of the individual atomic orbitals. You were introduced to the molecular orbital energy level diagrams. We write electron configurations for molecular orbitals as we do for atomic orbitals. In particular, the Pauli exclusion principle and Hund's rule also apply to molecular orbitals, and we start filling in electrons in the order of increasing energy levels. In addition, the number of molecular orbitals always equals the number of atomic orbitals that were combined. Finally, you saw that molecules are stable only if the number of electrons in bonding molecular orbitals is greater than that in antibonding molecular orbitals. In the concluding lecture of the module, you will see how the bonding theories you have learned so far explain resonance and delocalization in molecules like benzene. Thank you for your attention.